In this next chapter, we're going to be looking at stereochemistry, and we'll be looking at three-dimensional stereochemistry. So this is a little bit different than what we've looked at so far, where we have examined cis and trans stereoisomers of alkenes, or cis and trans stereoisomers of cycloalkanes. In this next chapter, we're going to be looking at stereochemistry that involves three-dimensional structures. We need to get a little bit of vocabulary out of the way. We're going to be talking about enantiomers, which are non-superimposable mirror images. So I've got two molecules here that I've built, and notice that we have a carbon in the middle, and then we have a red, a white, a blue, and a green ball attached to it. So this represents four different groups that are attached to this carbon. So these carbons then are what are called chiral centers. Chiral just means handed. And if I look here, notice that I've got the white balls both pointing up, and the red balls pointing toward the camera. Now notice that the blue ball for the left one is on the left, and for the right one, it's on the right. So these two molecules are mirror images of one another. But I cannot superimpose these molecules on one another. When I try to do that, I see that they are different. The same thing happens with your hands. Your hands, you have a left hand and a right hand. They're mirror images of one another, but you cannot superimpose one on the other because they're different. So the same thing is true for these molecules. So we need to be familiar with this stereochemistry to be able to identify chiral centers, and we need to be able to assign the stereoisomer designation for these types of molecules. It's the same thing that you would do if you were trying to assign, is that a left hand or a right hand? So let's work a couple of examples. Let's look at, if I have a carbon and in the background I'm going to put hydrogen, and in the foreground I'm going to put a methyl group, and then over here I'm going to put an ethyl group, and then over here I'm going to put a bromine. So notice I have four different things bonded to this carbon atom. I have hydrogen, a methyl, an ethyl, and a bromine. So if I just sort of look at this, the perspective that we're looking at with this is where hydrogen is in the background, the methyl group is in the foreground, and then I have the bromine and the ethyl group over here in the plane of the paper. That's the perspective that we're drawing of this molecule. So the way that we assign whether or not this is so-called a right-handed or a left-handed stereoisomer is with the Kohn-Engel-Prelog rules. So we look at the ranking of all four substituents and we put the lowest priority one in the back. Typically that's going to be a hydrogen, but not always. So if I put the hydrogen in the background, then I look at the remaining three, and I notice that bromine has the highest priority. The ethyl group has the lowest priority. The methyl group has the lowest priority. And this gives me a counterclockwise rotation. So this is the S stereoisomer. If I were to draw the same molecule, but the switch places between the bromine and the ethyl group, notice that now I have the bromine, which is the highest priority group, ethyl, which is the next highest priority group, and the methyl, lowest priority group. This gives me clockwise rotation, and so this is the R stereoisomer. So to assign the stereoisomer, we have to put the lowest priority group in the background, like this. If I put the hydrogen, the white ball, in the background, then I'm looking at, does this give me clockwise or counterclockwise rotation? So as you're learning this, it'll be really helpful for you to build the molecules and actually look at the molecule so that you can assign the R and the S stereoisomers correctly. So let's look at a few more examples. In this top molecule, we have the highest priority group is iodine. The next highest priority group is the ethyl, and the lowest priority is the methyl. So if I want to put the hydrogen in the background, I need to view this molecule from the left. That's where I want to look at this. So if I imagine doing this, I need to turn the molecule so that the hydrogen is in the background. And then I'm going to look at the iodine. So if I turn this, that's going to make the methyl group come over to the right side. So I'm going to have carbon, methyl group, or ethyl group. And the iodine is going to be down here. We're putting the hydrogen in the background. And then we're putting, and this methyl group is still in the foreground. It rotates up to the foreground. So if I look at this, this is my background right here. See that I have counterclockwise rotation. So this is S. And we need to be able to visualize this, not just by redrawing it, but by looking at this molecule. And we can see that the rotation would be in this direction right here, coming out, back, up and out, back. And if I keep doing that and I turn it so that I'm looking at it, I see that it's counterclockwise. The other thing that you can do is assign groups to these. So for example, I can say, okay, this is my hydrogen group, this is my iodine group, this is my ethyl group, and that's my methyl group. And then I can turn this, and I can see that I get counterclockwise rotation. So you can tackle these problems with a couple of different methods. All right, let's look at these next two. These are the sawhorse projections. And remember that in these sawhorse projections, this back carbon is in the back. And we're looking for what is the chirality of this back carbon. So in the back, the hydrogen is coming up. This is coming out toward me. And then both of these are going down into the background. Okay? So the highest priority group is the bromine. The next highest priority is the ethyl. This is an ethyl group here. And then the lowest priority is the methyl, if I've already put hydrogen, which is the absolute lowest priority, in the background. So I go from bromine to ethyl to methyl. And this rotation looks like it's counterclockwise, doesn't it? But that's because the hydrogen is up. I need to look at this from the bottom. So if I'm looking at this from the bottom, I'm not going to see counterclockwise rotation. I'm going to see clockwise rotation. So this is R. Let's look at this next one here. Notice that this is the same molecule, but that may have a different stereocenter. So here again, I'm looking, this is my back carbon right here. And this hydrogen is pointing sort of down and away from me. So I've got rotation from highest to lowest priority. It looks like this. Now if I'm looking at this from this angle right here, I can see that this is counterclockwise rotation. And so this is S. All right, 2 more examples. We've got substituted cyclohexane rings, where I'm looking for the chiral designation for these starred carbons. So I want what is the chirality of this carbon right here. Now notice that the lowest priority group is the hydrogen, and it's pointing up. Okay, and then using the Kahn-Ingold-Prelog rules, I know that this front carbon is the next highest priority because it's attached to the bromine, and then this is the next highest, and this is the third highest right here. So I'm going to have rotation that looks like this. That looks like it's clockwise rotation, doesn't it? But where is the lowest priority group? Hydrogen is up. I need to look at this from the bottom so that the hydrogen is in the background. When I do that, when I look at it from the bottom, I'm not going to see clockwise rotation. I'm going to see counterclockwise rotation. So this is S. That stereo center is S. Again, we're looking for this blue or this starred carbon. What is that? Was the chiral designation for this carbon? Again, we've got the hydrogen is now pointing in this direction right here. This is the front. This is my highest priority group. Next highest priority group. Okay. Now I want to look at this from the top left. So I'm looking at it from this direction right here. When I look at that, I'm going to see the rotation as drawn. And so this is clockwise rotation. And with clockwise rotation, we get R.